We can start. All right. Good afternoon. All right. The last time we talked about substructural current. It's not a new topic for you. Let's still very briefly review some of the basics and conclusions about the substructural current. Right? The substructural current is really a leakage current, so I add this word leakage to emphasize that. It's a really leakage problem we're talking about. Specifically, in this log ID versus VG case, we can concentrate on this point, that is the current IDS at VGS equal to 0. That's a problem. Okay? Now, we want to keep this leakage current small. There are two things we can do. One, we can pull VT up, pull far away from 0 VG. That's undesirable because it hurts our ID set. The other is we can make this slope large, which means make the swing small. Swing is defined as 60 millivolt times 1 plus C depletion, not defined this way, defined as the number of millivolts per decade of change. But it can be related to the design of the device in this simple model. It's 60 millivolt, 1 plus C depletion over C aux. Because small swing is good, therefore thin oxide is good, thin C aux is good, and for this reason, for this phenomena, only a large WD depletion is good, right? W depletion is good. These are good. Large W depletion is bad for other problems that we will actually see today. Okay? But it's good for large W depletion is good for swing. We talked about another thing last time. It's known as the gate-induced string leakage. That's usually observed on the same plot when VG is very small, or for this purpose of studying this, you could even apply negative VG, of course. Current start to increase again, and that current is explained by band-to-band tunneling. It's called gate-induced string leakage, or GIDO, as the acronym, and often used in literature, GIDO. Right? Any questions about these two things? The GIDO current and the substructural leakage, both are leakage currents. All right.
Yes, I have a question.
Yes.
It's on the page 8-8-8.
All right.
Yeah.
That's very good. Maybe you can turn to page 8-8. It's the last slide of last lecture, which I actually did not get to, so I was going to spend a little time on 8-8. But please ask the question first, Dean.
So are these curves generated by a 2D simulator, or you draw it randomly?
This is drawn by freehand. So if you see some detail that bothers you, it's probably because it's a freehand drawing, therefore does not look perfect, although I don't immediately see big problems. So let me go through this set of curves, and then maybe you can ask questions, all right? Okay. As I said, this is the last slide of the last lecture, but I did not have time to go over the slide with you. So let me go over with you right now as a review of the new problem that we introduced at the end of last lecture. The new problem we introduced is called either VT roll-off or called drain-induced barrier lowering. You remember those two terms now? Remind you, those two terminologies we use. We introduced something called a VT roll-off, also called drain-induced barrier lowering, or DIBBLE, drain-induced barrier lowering. Both of these also called short channel effect, all right? So there are three names that we could be talking about this. Short channel effect may also be used to refer to a larger class of problems, but could be called short channel effect, all right? But these three things very often are used interchangeably. You can always argue they should not be used interchangeably, but often they are, and does not cause much problem when they are used interchangeably. All right. the one way to understand this problem, and I recommend to think this way, is look at the energy band diagram between source and drain. So source and drain with channel in between. And I draw a case for long channel, a shorter channel, and even shorter channel. All right, let's first look at long channel case. The top curve is drawn for certain VG, probably VG at flat band voltage. So what we see is there a barrier, maybe 0.8 volt between the source and the drain that stops the electrons from the source from flowing into the channel. All right? Okay? And that's why we don't have an inversion layer, because electrons from the source cannot get into the channel. Right? If we now, and we need to apply certain voltage to reduce this barrier, and that voltage required is called a VT. All right? Now this barrier is not affected by a VD. If we apply a VD, you see, we just have a large depletion region between the drain and the channel. We don't have any, don't see any change on the barrier between the source and channel. Is that right? So that's why in long channel transistor, the barrier, when we say the word barrier, we mean the barrier between the channel and the source. The barrier is independent of what happens at the drain, specifically independent VD. Next, if we make the channel a little shorter, not too much shorter. If we make too much shorter, we're going to be in trouble. But to make it a little bit shorter, as you can see, we still reach the full maximum, and perhaps I'm not quite sure what I'm trying to say here. Let me just say that it didn't make there's still flat portion, let's say here, all right? So we don't see a channel length don't see a drain-induced barrier lowering, all right? We still have a pretty good, well-established barrier before we enter into the regime where the energy band diagram drops toward the drain. And if that's the case, if we apply certain VD, we probably will still not reduce the barrier compared to the original barrier height. Of course, there's the intermediate region. I'll come back, but you will see what I'm trying to get to in a moment after I tell you the third case. So in this intermediate case, we can argue, well, perhaps, all right, I'll change my case now. I may change my case this way. All right, for that intermediate case, perhaps the barrier is not affected by VD, but it may still be affected by VD if VD is large enough, right? If we keep increasing VG, at some point, the barrier will be smaller than what I drew in the black line, all right? So in this intermediate case, if I may add a word, barrier is not, let's say, affected at low VD, such as 0.1 volt VD perhaps does not affect it, or even 0.5 VD may or may not, but it would be affected. It is affected at high VD. Do you see that possibility? It is affected at high VD. Do you see that? You see, when VD, we apply a little bit of VD, well, maybe we still have the full barrier. But if I keep increasing VD, can you imagine eventually this barrier cannot be sustained, right? The following language may help you understand. If so, then by all means use language, but I don't really like that language. That is, you say the depletion region from the drain, from the source touched, and that's why the barrier cannot reach its full height. Can you visualize that? Right? All right. So this is the beginning of the drain-induced barrier lowering. Drain-induced barrier lowering. All right? Now, why do I show you a third case? The third case is that if the drain is even shorter, can you see that the barrier would not even reach that full height, even at very small VD, such as 0 VD? Just the built-in potential can already cause the two depletion region to merge. Can you see that? Can you visualize that? Yes? So this will be the extreme case, all right? So the middle case, sometimes called the drain-induced barrier lowering. And because the VD plays a role here. In this case, some people like to say, well, this is not called drain-induced barrier lowering. This is called channel length dependence of the threshold voltage. I don't like that picture. Well, clearly, this is also representing the effect of drain on the VT as well. So that's why the name sometimes people don't quite agree what they mean, but it's better that you have your own understanding of what we're talking about. The fact is that when the channel length is very small, then the barrier height is affected by both VD and by L. And that's what we'll be talking about. That the VT is function of VD and L. Question?
Is tunneling important, as important, much less important from source to drain through the short
banish
channel?
that thought from your mind right now. We're not talking about tunneling. Eventually, tunneling can be important, but here in this model of the short channel effect, tunneling does not enter whatsoever. All right, tunneling is very strong impact of width of these tunneling regions, and tunneling kind of comes sort of in the future. Up to today, tunneling plays negligible role in the MOS transistor physics. So when you think about short channel effect, drain-induced barriering, they have nothing to do with tunneling. On the other hand, the kind of picture we drew, now if this field is, this barrier is thin enough, there will be tunneling. And we think in the next few generations of technology, we may look at some situation like that. But right now, it has nothing to do with short channel effect. Yes?
I understand that the effects are two completely different things, but I'm wondering if the currents are comparable.
You don't have to worry about it, not thinking about it. I meant is that the tunneling current is much smaller than the current flowing over the barrier, which is what we've been talking about so far. All right? Okay. But in the future, of course, 10 years from now, well, we'll have to think about that. Yes, question.
What's the length of L at which short channel effect becomes important? What
length is so-called short channel effect becoming important? There's no simple answer to that. You know, when channel length was 1 micron, the short channel effect is pretty important too. In the sense, people have to do some special things to try to design to avoid that. Certainly, 0.5 micron, a lot more work has to be done to prevent the short channel effect. 0.2 micron, 1/4 micron is even harder. But right now, we're designing 0.18 micron. We can still do it, and we believe it can even be done at 0.1 micron and somewhat shorter than that. It's just getting harder and harder. There's no point at which you can say you just cannot do it, or it's long enough. You just don't have to worry about it. And in a way, that's what we're going to try to understand. What determines the short channel effect? If the goal from the desire to reduce the chip size, increase the packing density, reduce the chip cost, we want to make transistors smaller and smaller. What can we do to make them small? We cannot just say, we draw a line here saying, no, don't scale below this. No, we want to keep scaling. So what can we do to allow scaling to continue? So we'll talk about this in this and next lecture. Continue your question.
So overcoming or reducing short channel effect means that there is no drain-induced barrier lowering. So there has to be some region where the potential difference, the barrier is at the maximum value.
Go on.
Is that what you try to achieve?
Yes, it is. Yeah, that's correct. All right. Okay, great. Yes, comment, question in the back. The device usually assumes symmetric, but the bias is not symmetric, you see. From the energy band diagram, you can see the bias is not symmetric, but the structure is assumed symmetrical. Yes, that's usual analysis. That's interesting discussion. Maybe we should save this for discussion perhaps today after the first lecture in the discussion set. Maybe we can bring that up and we can all hear how would you like to make the source not symmetrical, how you think you can help this. But first let's understand the basics, which is what the topic of this lecture. Then we can start talking about how to go beyond the practice, general practice, and see how you can make them better. All right? Okay, any question about this description of the problem? This is one way to think of a problem we're dealing with. All right, let's review some of the figures. Here, figures plotting log ID versus VG. So very often what you notice is that as you increase VD, the curve is shifted to the left. And this is because VT gets smaller, right? As a result, the leakage current at VG equal to 0 is larger. That's a problem, okay? All right, and again, just to make this curve prettier, I want to make it flat, right? Don't want to make it not yet, okay. All right, and let's see what else. All right, so this shows how VT can decrease with increasing VD. What about this curve? This curve shows VT as a function of L can also drop. How do you understand that? Well, think about this term picture, is that right? You see what we're saying? Yes? If the channel length is short enough, even without applying large VD, even with 50 millivolt EV, in fact, even 1 millivolt is fine because the built-in potential is larger than 50 millivolt, right? Only reason we apply 50 millivolts is we need a little bit of VDS in order to measure ID. And from ID, we measure VT, right? Okay. So 50 millivolt has no significance. 1 millivolt is fine, right? We're going to still see a VT drop as we reduce the L mean. As we reduce L, channel length. You see what I'm talking about? All right? So as you can see, you can understand the effect of L and understand the effect of VD in a similar diagram. Right? Yes? All right? So in that sense, these two things could be thought of as having the same origin. On the other hand, many people would like to use different names to call them. If they use different names, they will call this Dibble. They will call this VT roll-off. Or call this short channel effect. You see, this is where I felt this usage is a little bit too narrow, right? If you limit the short channel effect only to this, not to that, that's a little bit too narrow. But you can see why some people want to do that because this has to do with channel length, L, the short channel effect. But this is strong function of channel length too. Very strong function. In the sense that if I make channel length a little larger, Dibble goes away. So how can you say Dibble itself is not a short channel effect? So sometimes the terminology can be confusing. Different people use it to mean different things, all right? Okay. So that's why I prefer to just call this VT roll-off. I think it's better. And maybe think of short channel effect as referring to both of these. That's a pretty good usage because these two really goes in hand. If you don't see this happen, you're not going to see Dibble either, or not strongly. It's really the same thing. So both are short channel effects. That would be my preferred way of using the terminology. Is it okay? All right. All right. Again, some terminologies. VT, a long channel, is called a VT0 from now on. There's a new subscript 0 to refer to long channel transistor, just so that VT just means, well, all right. Then define delta VT. Often you see delta VT is defined as you take a long channel transistor VT minus the VT at a certain L. It doesn't have to be, say, L mean, a certain L, all right? And that quantity is typically a positive number. That is, as channel length is not infinite, then this VT is always smaller than the infinite L VT. Therefore, delta VT is usually a positive number. Later we will show you special cases when it's not. But that's the picture we want to keep today, all right? And finally, what we're showing here is this is important because very often people will say that we can only accept a 0.1 volt decrease in VT. Below that, VT will be too low, leakage current will be too large, and this actually would define what's the shortest channel length we can use, and that's called the minimum channel length, L mean, all right? Now, whether it's 0.1 volt, 0.15 volt, that's arguable. But the idea is that this consideration often determines the minimum channel length that is acceptable in the circuit design. All right? Another consideration that can determine a minimum channel length is that at minimum channel length, dVTDL should be also small. In other words, not only this this delta VT should be small, the slope here should also be small. The reason for that is that, manufacturing variation always give us some uncertainty in the L that we get on the chip. Now, if this slope is very large, it simply means the manufacturing variation will give us large variation of VT. You see what I'm saying? Right? And that's certainly not acceptable. So, to some extent, this is probably even a better way to define L mean or to determine L mean than that. But in the literature, you often see people emphasizing delta VT more than delta VT, dVT dL. All right? But again, if you understand this problem, you can argue and maybe even mathematically can even show at the end of today these two things may be related. All right? Okay. All right, so that's the basics. And what we're going to do next is a theoretical model to put this in a quantitative manner so we'll get a better understanding. Now, Jean, do you still have questions about the slide? 8.
Yeah, okay, just some comments. That
yes,
this
please.
curve right now is for the substitution region. Yeah, so the VGS is less than threshold voltage, right? Okay. It makes sense to me that for VD just like here the shorter device, the VD increases, then there we cannot see any significant barriers lowering by
Yes,
this
it's already
VD.
in the, sorry.
It is in the substitution region.
This is in
right.
the substructural region, yeah.
Yeah, right.
You say you don't see it? You don't see barrier lowering?
Mm-hmm. But just from your curves, there's no significant. But I see that in how to say that in.
Or maybe I'll see. This is your question because you began by asking me where this hand drawing or where this Medici Rios 2D simulation. Maybe you're saying from your experience you don't see this when you do a Medici type of 2D
but
simulation.
actually, the barrier is more defined by the VG, the gate bias instead of the VD, right?
Absolutely.
Okay. And also in the substitution region, the minimum potential surface potential is not in fact the point close to drain, but a little bit apart from drain. Is that true? Right.
That's fine. That's why you can see I emphasize this peak potential. I didn't say right at the drain. If you're looking at the metallurgical junction, it may be here, right? Metallurgical may be here. We don't care what it is at this point. We only look at the barrier height at the peak. So certainly I didn't argue that we should be looking at the barrier height right at the drain. If this is how you define the drain, this is the metallurgical junction. No, this is the peak. So that part I agree with you. The important barrier here is the difference between the EC of the source and the peak of this whole plot. That's the only barrier we need to look at.
Okay, so this barrier in fact is not a source junction barrier. Instead, it is a source to channel barrier.
Absolutely, it's a channel barrier. That's the word I would use, channel barrier. All right. Okay, I think that the lecture later will clarify this. All right. All right. All right. So this is not where I thought we were going. But I'll very briefly mention this. This is not where I'm going to spend time today. This is a section 5.2.1.2 called charge sharing model. Some of you probably have heard of this before, and I don't plan to spend a lot of time because this is a qualitative model. It is a good model. It is helpful. Sometimes help you understand certain qualitative things. Therefore, I think it's a good model to remember and to know about. But it's not a useful model as a quantitative model. So I think most people don't use this as quantitative model anymore. It is a qualitative model. So I only have one slide I think to talk about this. Then I'll tell you the other models way to think about this VT roll-off and the Dibble effect that's more quantitative. All right. So in this charge sharing model, this is the way to understand that. You say, we look at this cross-section of a transistor. There's the gate dielectric, source, and drain. and we added two other lines. That's the boundary of the depletion region. There's a boundary of the depletion region under the source, boundary depletion region under the drain. Is that right? Yes? Okay? And then we even had a boundary of depletion region under the channel. In the case of channel, of course, the step is only XD max. All right? So this is a highly simplified picture. Just draw a curve like that. You can probably visualize. We pick the depletion region width here, and then draw here this portion where probably assume a cylindrical shape of the junction, and therefore draw another quarter circle with a larger VDS. The VDS is equal to junction depth plus X depletion. Is that right? Yeah? Do the same thing on the drain side. And in the channel, we draw a line, horizontal line, at the depth of XD max below the surface. Okay? You see how that's established? All right. Next, the argument goes that let's pay attention to a trapezoid formed by this 4-point, A, B, C, D. Point A and D is obvious. You see where they are formed. They're just formed by where the junction intersects the surface. Right? B and C are formed by the intercept of this X depletion, XD max line, and this source depletion boundary. Similarly, C is determined by the intercept of the channel depletion region boundary and the drain depletion boundary. You visualize that? That's the result. We now have 4 points, A, B, C, D, and they form a trapezoid. It's okay? Next. The model goes on to argue this way. It says, the basic model says Vt is equal to VFB plus 2 pi b plus charge in the body over Cox. This model says charge in the body should only include the charge in the body in the trapezoid, Q n sub of area of this ABCD times W, rather than what? Rather than L times W, L times W times the XD max. Not by this. You see, that would be the normal interpretation of QB. Normal interpretation of QB will be the density times L times W times XD max. That will give us a charge in depletion region. Is that right? Because that's the volume of the depletion region. This model is just a model. You can judge yourself whether it's a reasonable model or not. Says, well, that's assuming all the charge in this region, this rectangular region, create electric field in the oxide. Remember what this term is? This is the Vox term. Remember that? Right? So it argues, why should a charge at this part, let's say, create electric field in the oxide? Why doesn't the charge create electric field that terminates in the drain junction or in the source junction? Right? Yeah, does this charge belong to this PN junction's depletion region, or does it belong to this vertical portion of the MOS system? And so no one can answer this question quantitatively. This model simply says, well, let's assume all the charge that falls into the trapezoid ABCD creates Vox. All the charge for outside the trapezoid ABCD only creates field that terminates in the source and drain. All right? Now you can determine whether you like it or not. That's all. All right? Yes. Okay, we're not going to solve anything. That's the beauty of this model, is that this immediately will give us equation for Vt. No more solving anything. All right. So if you're going to sort of propose some modifications to further improve it, maybe we can talk about it after we see this basic model. Then you can say how you would like you think we may be able to improve that. All right. Okay. Let's see the basic model, charge sharing model. What does that? It just says we only use the charge in the trapezoid to represent QB. So all you have to do is figure out what is the area of the trapezoid as function of junction depth and channel length and things like that, and X depletion, right? And XD max. And if you do that, you end up with this equation. All right? It's not too bad, actually. It's this. All right? That is, compared this versus the case with a rectangular case versus a long channel case, you will see a modification. The VT will be different by among delta VT. And delta VT can be given in this manner. Right? You follow what I'm saying? All right. And so I will not spend time with you in looking at this equation, but I'm going to spend time with you looking at qualitatively how you expect this behavior to be. And I can tell you that this model does correctly predict this behavior. All right? Therefore, it's a useful model. Quantitatively may not be accurate, but it does qualitatively give us all the right trends. Now, for example, just from what you know, delta VT, of course, is really the difference between the trapezoid area and the rectangular area. Is that right? Rectangle area and trapezoid area. The difference is responsible for the delta VT. Is that correct? So now I'm going to ask you, this delta VT will decrease when each of this quantity does what? What I'm really asking you is that the difference between trapezoid and rectangle is going to disappear when what? It's going to become smaller, right? All right? The difference between these two model using rectangle versus the trapezoid will be smaller when L is large. Do you agree? When L is large, whether you're talking about rectangle or trapezoid, the ratio of these two is very small, right? Yes? The difference is very small, correct? See, that's the correct thing. Because physically, we also, it's true. It did agree with observation. When channel length is long, we don't have any channel length dependence of VT. Remember the VT roll-off picture? Right? And when VT decreases, there should be less of an impact. Why? Because, look, at the other way is probably more clear. When VD increase, that means the depletion region under the drain will be larger. Is that right? If you do that, the trapezoid area becomes smaller. Can you see that? Can you see that? How about when the doping concentration increases? The doping concentration increases, all the depletion regions become thinner. Think the extreme case of zero depletion width everywhere, depletion region length everywhere. Do you have any difference between the trapezoid and rectangle? So it makes sense. When doping concentration is stronger, the short channel effect is weaker. That's right. That's good. That's good. All right? What else can improve the short channel effect? How about when TOX decrease? TOX you may not see because it does not come from the difference between the trapezoid and the rectangle. It comes from the fact delta VT also has the COX term in it. You see? The trapezoid and the rectangle difference tells the difference in the QB, but there's also the COX term here. If the COX is very large, meaning when TOX is very thin, then it doesn't matter if QB changes due to the short channel effect, we have very little impact on VT. All right? You may say this is, maybe you say this is cheating. Turns out it's not cheating. Let me tell you, of all the possible solutions to minimize short channel effect, using thinner oxide is the best one, the most practical one. Because we want thin oxide anyway. It doesn't hurt anything. We always want to use thinnest oxide. Anytime you're not using thinner oxide, you're getting worse short channel effect than you need to. All right? Doing other things actually are harder. So this turns out to be the best thing to do. When you want to improve short channel effect, the best thing you want to do, make sure you're using the thinnest oxide. Okay? Junction depth, thinner is better. Can you see that? Right? If junction depth is better, xj is smaller, then the whole radius of this curve is better, then the trapezoid difference and rectangle difference is a little is better. Is that right? Okay. So qualitatively, this gives us the correct effect, and in fact, we can even add one. Let me add this one. What happens if we add a VBS? Okay, let's say body bias. When body bias, what's the impact of body bias? If body bias increases, now add a body bias, all the junctions are reverse biased to the substrate. Is that going to give us a worse or better short channel effect? Worse short channel effect. Absolutely right. You're right. So if we decrease the VBS, if we don't have VBS, right, it's better for delta VT. Good. So you now have a thing that you can use the charge sharing model to answer those questions. Okay. Any questions about charge sharing model? Back to how about you in the back? Now maybe you can finish the statement and the comment you made earlier. How would you propose to do differently? Right. Now that you have seen how it's done, do you have any idea? Reasonable, huh? Okay. All right. Good. At least you like it. But as I said, really no one can argue this trapezoid is right. We don't really know. This is just qualitative model. All right. Okay. Is there a comment or another question? Yeah, question.
I'm wondering how well does it model the drain-induced barrier lowering, because when the barrier is lowered, right, the current increases exponentially, and does this model really predict that?
That's exactly the right point. This is quantitative right, it's not quantitatively right. All right, so let's then move on to the next model. But this is the one that most engineers know. What we're teaching you next, I would say most engineers don't know about it. All right, you're going to be way ahead of most engineers. But most engineers think about short channel, they still think about the charge sharing model. All right, so you should know it too. All right, just so that you know what others know. It does, yes. Yes. Well, let's see. So Jing actually likes this simpler model better for that reason. We'll see. All right, let's continue. Let's look at another model. This model is a new section in the textbook 5.2.1.3 and two sections together. And the topic is a quasi-2D model of Dibble. All right, I think it's a more quantitative model. I think it's a better model. It works this way. You know, actually, perhaps even before we get into this mathematics, which is a little bit messy mathematics, let me emphasize the picture I show you. That is using the energy band diagram to understand short channel effect. That actually is the first and foremost thing I like you to take from this course. Charge sharing model does not even invoke the concept of this picture of this energy band diagram. Does not require to think that the change in the VT is a result of a lowering of the barrier. And I think that is really not good. So I really think that just by having this picture in mind, by the way, I think you can already answer the earlier list of equations. All right, I will not do this with you, but I believe you are already able to do it. But today we're going to actually to analyze this more quantitatively, in the sense we're going to find an equation that actually describes the whole shape of this energy band diagram. If you can do that, then of course we'll be able to figure out how much this peak is lowered by Vg by L, by Vd by L. Is that right? Is that right? So that's what we'll be doing in the next half an hour. Is that right? Okay. But even without doing it, just by thinking about it, I believe you can already tell me, let's say, if I bring the VL closer, should this barrier be lowered? The answer is yes. We have done this at the beginning of this lecture, right? Okay. But now we're going to actually derive an equation for this whole curve. All right? Let's see how it's done. We do this. First, let me point out the proper way of solving these is to solve a 2D Poisson's equation. But solving 2D Poisson's equation is very difficult. All right? So instead, we actually make approximations, still solve something the like Poisson's equation. We call that quasi-2D model. And we actually don't start with a Poisson, the standard Poisson equation. You can, and other people do that, and the result is very similar. But we start with the Gauss law. But we end up with equation looks like Poisson's equation. You will see what I mean. So let me set up the Gauss box with you. The Gauss box is set up this way. We take one point in the channel, that's Y, right? We draw that line. It's one boundary of the Gauss box. Is that right? Yes, I guess this is a Y, right? This is the point Y, let's say. And then another point, Y plus delta Y, is another boundary. Okay, I should write this in larger. Okay, one boundary is Y, one is Y plus delta Y. Is that right? Yes. The top boundary is the oxide interface. Is that all right? All right. The fourth and last boundary is the trickiest one, and let me call that X depletion. Later we can qualify that to say maybe it does not have to be X depletion, maybe there are other things, we can talk about it. All right? Qualitatively. Right now, let's call it X depletion. Is it okay? All right? Let me tell you what I really want. Maybe right now I'll tell you what I want, and then we say why X depletion is approximation. What we're really looking for, we're looking for a boundary down below where the electric field is zero. Now choosing depletion region XD max, of course, is fine, because at the edge of the depletion region, the electric field is zero almost by definition, right? The depletion region has ended. We'll get into the neutral region, so there's no electric field. Is that right? Is that right? But that's not such a good choice, actually, for two reasons. One is that how do we know this X depletion is not going to be pushed down by the junction? Right? This is what Jane was asking earlier. How do we bring the junction depth explicitly? We cannot. We just have to qualitatively think. Well, if we make the junction deeper, you're going to push this down also. We know that, right? We don't want to use it as X depletion plus Xj either. We don't want to do that either. X depletion plus Xj either, all right? The reason is that we also want this line, not only no electric field, we also want this to be more or less, not more or less, we want to be parallel to the surface in order to make this equation solvable. So that's one approximation. We have to find a line that's more or less zero electric field and more or less parallel to the surface. So as a compromise, we choose X depletion. All right? Okay. Later you will find, for several reasons, the choice is, well, I'll just stop there, okay? After you see how we use it, then you can always come back to discuss how good or how bad this approximation is. All right. Any question about the Gauss box? What we chose? There's the four boundaries. No? All right. Now, let's use the Gauss law. Now, remember, use the Gauss law. This is what we do. Well, first, let's look at some boundary conditions also. We'll be looking at the surface potential, the potential in the channel, let's say from source to drain. Surface potential at the source, phi s at y equal to 0, is equal to VBI. Now, when we do that, we automatically are telling us what is the boundary we're using now, boundary condition we're using. We're using a boundary condition that at the source, it's 0, right? Inside the source is 0. Therefore, inside this channel would be VBI. Actually, I beg your pardon. I take it wrong. I'm sorry. I take it wrong. Now, sorry. Okay. In the M plus source, here's emphasis. I forgot. We take phi s. All we know is phi s. We're asking what is phi s in the M plus region of the source. And let me tell you what the reference is. Reference is phi equal to 0 is the bulk. In other words, we're using the standard definition of chapter 3, our first month of lecture. Where do we take as the reference for the potential? We always take the neutral region of the body. Is that right? Yes? So if the neutral region of the P is 0, what is the potential of the neutral region of the M plus source? It's the source body built-in potential, right? Is that right? And there's no ifs and buts about that, because that's just determined by the doping concentration of the body and M plus source. You all know the built-in potential of p-n junction, right? Right? So this definition should be very clear. Not necessary even taken at the surface. You can take this in the bulk. Is that right? All right. So VBI is this point. This point potential is equal to VBI. All right? And here, phi s is equal to VBI. This is a very clear definition, right? In other words, we're going to find the solution for all along all this line. You see that? So we'll start right here. Any problem with this reference? Okay. So here's VBI. The reference is the neutral portion of the body. Question?
In your diagram, you have shown 0 and L as
that's a y. Y equal to 0 as a source. Y equal to L at a drain. So for y less than 0, for y being negative, the surface potential is VBI. For y larger than 0, you're going to start to rise. So y equal to 0 is here. This is y equal to 0.
So the L you use there is not the length of the gate. It's
that's right. In device physics, we always emphasize the channel. When we say channel length, we always mean this channel length. We don't care whether the gate is here or gate is here. Okay, in case they are different, we always talk about channel length. Okay. All right. The gate length is very important from technology consideration, from lithography, overlap capacitance. But when we talk about short channel effect, we always talk about this as channel length, sometimes called effective channel length. Good question. All right. Other questions? All right. So, well, you answer this question. At y equal to L, what is the potential in the M plus string? What is in M plus string? Start by the potential in the M plus source. You know that already. It's a little unusual, but I'm forcing you to think. The potential in the M plus source is not 0, it's VBI. Knowing that, what is potential in a drain? Given that drain source voltage is known, of course. So what is it? It's VBI plus VDS. Isn't that right? It's not difficult, right? All right. Good? All right. Very good. So, by the way, by doing this, you can see there's no problem with a back bias. If a back bias, of course, this becomes VBI plus VBS or something, right? To some extent, you know what I mean? Yeah. In other words, clearly you understand. If we use 0 as the potential of the neutral body, then the potential of the M plus source is very easy. What it is, right? There's no question. All right. Now let's apply the Gauss law to this Gauss box. Gauss law says we should take electric field coming in or coming out of one boundary. Electric field coming out. By the way, I draw the arrow in this direction because I'm taking the knowledge electric field typically is in this direction, right? Why? Because we put positive voltage on the drain, right? Right? So typically the arrow is going this direction, happens to be the positive y direction, yeah? So the Gauss law says all the electric field going out of all the boundaries, out of that word, is equal to the charge inside the Gauss box. So let's first look at electric field of flux going out of the box at y equal to y plus delta y. That's equal to the area of that boundary. That's xd max, height, times w. W is the dimension normal to the screen, normal to the paper. Is that right? Times ey at that point, evaluated at y plus delta ey. Yeah? That gives, and times epsilon. That gives us the electric flux flowing out of that boundary of the Gauss box. Make sense? Yes? Yeah? Subtract electric field going into this box. Is that right? Yes? Subtract this electric field going into the box is equal to xd max times w times electric field evaluated at y times epsilon. Make sense? Yes? Okay, so we took care of two boundaries. Well, I have to look at the other two boundaries. The third boundary is the interface. How would you figure out the electric field at the surface of this box? That is equal to Vox equal to the voltage related to the electric field in the oxide. Isn't that right? If you know the electric field in the oxide, multiplied by the raised by 3, or divided by 3, you get electric field in the silicon surface, right? And what determines electric field in oxide? It's just Vox divided by Tox. Is that right? So Tox is here. What do you know about Vox? What do you remember as giving us Vox? Vox is always equal to Vg minus VFB minus phi s. Where does this come from? This comes from the fact Vg is equal to VFB plus phi s plus Vox. Remember? Remember? So very nicely, we express this electric field in terms of phi s. Phi s is going to be our unknown anyway. We're going to solve for that. Are you still with me? All right, so this is the electric field in the oxide. Multiplied by the oxide epsilon, that gives us electric flux. Is that right? And times the area of that boundary of the Gauss box is W and delta Y. Do you see where delta Y comes from? Delta Y is this dimension, delta Y. Yes? W times delta Y, do you see that's the area of that surface of the Gauss box? Any questions? Excellent. Last, and the fourth boundary. What's the electric flux coming in or out of that boundary? 0. Because we pick it that way, remember? We chose the fourth boundary so that there's no electric field. Is that right? Got it? All right. Now you can also see why this fourth boundary also have a uniform depth, not function of y. Because we're assumed this Gauss box is the same height, not function of y. If these are functions of y, we cannot write down an equation that we can solve analytically. That's the problem, right? So we chose XD max thinking that's pretty good approximation. Okay? All right. Right-hand side should be all the charge in the Gauss box. All right? All the charge in the Gauss box. Okay? Now, remembering that this is a, we're looking at a model for VT, right? So we're looking for the substructural region. So there's really no inversion charge, right? It's really just dopant concentration, dopant density, right? So it should be equal to the volume times Q times N sub. And volume is equal to delta Y times W times XD max. Do you agree? That's the volume of the Gauss box. You with me? All right, very good. So here we go. That's the model. Now, we can simplify this by crossing out all the W's. All right? And just by crossing out the W's and take away this parenthesis, we already got this next equation. Very simple. As you can see, we got epsilon s, XD max. Sorry, we also made one change. What change is this? Okay, it's this too. If you compare the first two equations, what do you see? If you use Gauss law, you see the difference between the first two equations is difference because there's minus sign between the two. It's simply equal to dy times delta y. Take a look at that. Ey at y plus delta y minus ey at y. What is that? It's dy times delta y, isn't it? Right? So that's why the second step is now looks much shorter, second equation. The second term, no change. We kept everything in the second term. Right? Right-hand side, we kept everything, no change. Right? Next, every term now contains delta y. See that? Yeah? So we cross out the delta y term. All right? Yes? Now, we also did what? We also divided the XD max. Every term divided by XD max. So XD max goes away and appears now in this term, in the denominator of the second term. You see that? Yes? Now what else did we do? Similarly, we divided epsilon s into each term. Okay? Epsilon s, epsilon s. You see that? Okay? Now, so far, just mathematics. You can see no new physics, which is Gauss' law. After written down, we end up with this. What we have is really an equation very much like a Poisson's equation. It's dy dy. That's Poisson's equation. Is that right? Is that right? Okay. And you can even interpret, normally if you solve the Poisson's equation, you probably wouldn't have the second term. Just say dy dy. If this was homework, the first thing you do to analyze this, to solve this, you probably would say dy dy equal to the charge density rho. That's probably what you do first. So all we have done with this show you, actually, there is another term that's very important, which really is dx dx. I don't want to sort of to take this too seriously, but you really think about Gauss' law. Two-dimensional Gauss' law should have dy dy dx dx equal to charge density, right? The problem is that if we write it down this way, it's very difficult to solve. Not impossible. If you make enough approximations with boundary condition, you can solve by separation of variables, things like that, and some people do that. But we don't have to do it that way. But we still interpret as dx dx. You can see why it's dx dx. For example, you notice this term is inversely proportional to xd max. Do you see why that's the case? It's because any electric field Ex now, any Ex becomes 0 by the time we get to xd max, right? So the dx dx kind of makes sense, should be inversely proportional to xd max. Do you see this idea? Because whatever Ex we have, which is really Eox, right, will gradually decrease until it's 0 at xd max. So you can see this term actually can be interpreted as dx dx. But we came from this Gauss law consideration, all right? So we call this a quasi-2D analysis. It's really like a two-dimensional Poisson's equation. You can think of that way. Is that right? All right. So the physics is very simple, just Gauss law. Now, what really makes it attractive is that this equation has extremely simple solution. If it has a long solution, well, I'm sorry, it could have a simple solution, but it turns out, because boundary condition turns out to be complicated for this particular case. All right. The equation is very simple because it really has the form of what? If we change this dy dx, dy dy into d squared phi s dy squared. Can you see this change? Because electric field is the first derivative phi. So d dy is second derivative phi. Is that right? In other words, the slope of this curve is electric field. So the Laplacian of this phi s gives us d dy, right? So if we make that substitution, now you see this becomes a linear second-order differential equation in terms of phi s. Is that right? Is that right? And in fact, you even know the solution, the general solution. General solution is just exponential function, phi s is exponential function of y, that's all. Or hyperbolic sine cosine. You following what I'm saying? That's really great. Now, I wish we could stop here. Unfortunately, because the boundary condition has to be hyperbolic sine cosine, and the parameter in front of hyperbolic sine cosine is very long, such that the math is rather messy, and we're not going to go through detail of the math. I'm just going to show you a few intermediate steps, and if you're interested in the detail, we have a reading, assigned reading in your reading, all right? It's a paper with the first author's name is Liu. You see that, arranged about where you're supposed to read it. We arranged that book more or less along the order of the lecture. So you will see we should be reading this paper if you want to see the detailed math. All right, but the solution, that's the reading. Copies have been given to you. You read that. All right, read this. And solution is this: is phi s is equal to some general solution, some particular solution, plus this is the general solution. All right? And don't worry about what it is right now. Let me just tell you that, and the reason we have these, voltage at at the source, and okay, okay. If you make the plot, what you will see is this is what you see. All right. This is the plot. For example, at the right at y equal to 0, we'll get VBI. If we continue to plot at the negative y, it's just a straight line because it's the M plus region. So in this M plus region, we just get a VBI, right? And as we go into the channel, we start to see this curve. By the time we get to drain, what do you think we will get? It's VBI plus VBS, isn't that right? What I want to say, right? And this shape is what this hyperbolic sine cosine gives us, right? Now you know hyperbolic sine cosine is like exponential, so that means if we are far from these boundaries, we'll be just getting no dependence on y. You can see that, right? Right? And yet, if we put these two boundaries very close, you notice the barrier becomes smaller and smaller now. You see that? So everything we expected, this equation will give us. And that makes sense, right? If you have this kind of hyperbolic function with this boundary condition, it has got to look like that. Is that right? And that's exactly what we expect this barrier to look. So I think this is a very useful picture, even if these details too complicated, but we'll be able to sort of, don't look at the detail, look at the sort of a simplified form of this analysis result. All right? The important thing is there's a characteristic length, little l, that shows up in this hyperbolic functions or exponential functions. This little l basically determines how quickly this boundary, such as the drain field and the source field, decays away. That's the meaning of this L, right? Anytime you see L in hyperbolic function of exponential function, that's the meaning. Sometimes we call it decay length, right? Right? And if you want to use the decay length here, it's not bad actually. This is the field decay length, but that's not a standard term. Okay, no one called that. I guess we are the ones that chose the name for this. We have been calling this just the characteristic length, so that's fine. Actually, come to think of it, calling this a field decay length is actually very good. You will see later this does give you a physical picture. Field is decaying. It's very important. And let me give you the sort of bottom line quickly now. We want this decay length to be small. We want the field to decay quickly. That way, the drain will not have much impact on the barrier in the channel. That's what we want. The problem, then the question is, how can we design a transistor so that the decay length is small? All right? Okay. So right now, let me just looking at this as a mathematics problem. We know there's decay length, the characteristic length, little l, right? And it came from the previous slide. This decay length is always square root of the denominator gives us the decay length. You see that? This is going to have the units of a second power of length, right? So that gives us the second power of decay length. So we take square root of this. That's called a decay length, little l. So we repeat it here. So l simply is equal to that, right? This is not new physics, just mathematics. The interpretation is new physics. We interpret this square root term as the field decay length. Has very significant physical meaning. So how we got it from the previous slide is just math, right? That differential equation will give us decay length. The decay length turns out to be the most important thing we learn from this model, is that there is such a thing that controls how quickly the field from the drain will decay away. If it decays away quickly, we don't have serious drain-induced barrier lowering. If it doesn't, we have serious drain-induced barrier lowering, right? So now we can already see what we need to have a good drain-induced barrier lowering behavior, meaning we want large or small decay length. Large or small? Small. Remember that, right? Small decay length is good, which means we want what? Zinc oxide. See? That's the same result you will get from the charge sharing model, but it's a totally different way. charge theory model, the oxide thickness coming just because the charge is divided by Cox. But here we show you actually the whole profile of the potential is intricately linked to Tox. Makes sense. In fact, I can give you interpretation why Tox makes so strong effect. Because the gate is a boundary condition. It controls the potential, surface potential. I'll give you a special case. If you think the oxide thickness is 0, of course, this is mathematically 0, right? Then shouldn't phi s be exactly equal to the potential of the gate? And the potential of the gate is independent of y. Can you see that? Right? That's why a thin oxide will try to hold the surface potential independent of y. You see? Do you see what I'm saying? If I can make the oxide very thin, surface potential will be very well controlled by the gate voltage at every y. In fact, if the gate oxide is 0, the surface potential will be equal to gate voltage. Since gate voltage is not function for y, there will be no drain barrier lowering effect. See what I'm saying? Okay. That's why when Tox is small, we have very short decay length, which is what we want. If depletion layer is thin, we also have very small decay length. Why is that? Well, you can say this is because the dx term is large, but that to me is still not that physical. It's more mathematical. Physical way to think about it is actually xd max and the gate oxide thickness play very similar role. A few lectures ago, I encouraged you to remember there's a back gate. This back gate and front gate are very similar in many rows. Both of them are coupled to the channel, just through two different capacitance. One through the gate oxide, that's Cox, and smaller the better, we already know why. And the other gate couples to the channel through another capacitance, another dielectric thickness. If thinner Tox is better, shouldn't smaller xd max be better? Exactly right. If you believe in this, then you have a chance of, thinking about new device structure that might give you better transistors. Mainly, you want to make xd max very small. Okay? That's why retrograde is good. Okay? If you use uniform doping, if you pick the doping profile, get the right VT, you'll find this is too large. All right? So it makes a lot of sense. xd max and Tox should appear side by side. Physically, they play the same role. I'll give you an example. Suppose the xd max happen to be equal to Tox, with the ratio of epsilon, of course. You can even see why ratio is here. We're talking about electrical thickness of the top gate dielectric, bottom gate, if they were equal. All right? If they were equal. Can you see that the impact of these top and bottom gates on the potential at the surface is basically the same, roughly the same? You have two gates that are equally separate from this interface. Why shouldn't these two gates have the same impact on the surface potential? You see what I'm saying? It makes sense, these two appear in symmetrical way. Right? So when you see this, you get a lot of confidence that the kind of model really makes sense. You start with a Gauss law, didn't consider all these considerations, and yet the results tell you things that really make sense. Right? So it makes a lot of sense. Okay, any question about its decay length? To make it even simpler, since we're always dealing with silicon and the silicon dioxide, at least up to now, the ratio is actually a constant 3. It's called a 3 Tox xd max, and that's it. All right? So, actually, the next two slides really just math. I really prefer that you don't even see any more math. Just remember now, this is our result. That is the way to get good channel length, get good barrier lowering, is to use thin oxide and small xd max. In other words, use small L. You can imagine what's missing here. Just later, next slide, you probably will find out it's not just L that determines the severity of channel length, the drain barrier lowering, but rather the ratio of L over capital L. Do you agree? It's a ratio of those two, right? right? That's only missing thing mathematically. Otherwise, you have already gotten a very good quantitative model of the G-induced barrier lowering. Any questions? All right, so let's finish this. Now, what's this top and bottom figure mean? Top figure is plotting the potential. Bottom figure is plotting the energy band diagram called as E sub C. Because we have drawn you several energy band diagram, right? Energy diagram is just the potential mirror image. That's all. Is that right? Okay. Now, if Kevin can help me kind of shift this a little bit so that they line up a little bit better. Let me think. Are they roughly? Yeah, they will line up. Kind of line this up a little better. It'll be more clear when it's just mirror image of the other. All right? Okay. Thanks. All right. So now just a little bit more there. If you make some approximations, you end up with this. Okay? Phi s is equal to some constant. Let's not worry about constants very long because boundary condition is complicated. It has to do with the VD, for example, the drain voltage, and VG. So it's equal to constant times hyperbolic sine y over L plus B hyperbolic sine L over L plus some kind of constant. And this characteristic length or decay length L is equal to 3 Tox XD maximum. So no news here so far. That's from last slide. A and B are functions of VG and VD. We're not writing them down because they're very long. All right? You can imagine that they're function VG and VD, right? You can kind of imagine that, right? And we already argued if L is much, much larger than the decay length, there will be no dipole. You already see that, right? Is that right? And specifically, one way to make that happen is to make Tox much, much smaller than XD max, right? Yes? Or even better is to make Cox much, much larger than what? Than C depletion, using the notation introduced in the last two lectures. C depletion meaning this capacitance. Is that right? Is that right? Right? So once you have seen this, I would like to introduce yet another, I am sorry, I wish you had caught me on that. No, this L being much larger than L doesn't mean this. We actually want both Tox to be small and XD max to be small. We're not saying we want one to be smaller than that. I am so sorry, all right? Beg your pardon, all right? All we want is we want this L to be much, much larger than this lowercase l. Is that right? Yes? So, and let me tell you, what we're really saying is that we want this to be thin, we want this to be thin, remember? And we want this distance to be large. We want the channel length to be large, right? That will minimize the dipole effect. We want this oxide thickness to be thin. We want the depletion region to be thin. We want the channel length to be large. Right? Now that you know those, what we want in terms of length, I want you to restate them in terms of capacitance. Isn't that what we want? Is we want the gate oxide capacitance to be very small, large. We want the backgate capacitance to be large. And we want, I'll introduce a new terminology here, CD, called the drain capacitance, drain to channel capacitance to be small. Isn't that this what we're saying? Drain to channel capacitance to be small, right? Isn't that what we're saying? If you agree with this, let me tell you, this is the model that I really prefer that you use if you're looking for a qualitative model. If you're not looking for quantitatively, how does dipole affect, how does Tox affect dipole, how does XD max affect dipole in a quantitative way. By the way, this is good quantitative model, all right? This is characteristic length, it's a quantitative model. The chart sheet model is not a quantitative model, all right? If you're not looking for a quantitative model, the 3-capacitor voltage divider is the best qualitative model. All we're saying is we don't want the drain voltage through the drain capacitance to affect the potential in the channel. That's what we don't want. When the drain voltage through the drain capacitance affect the channel potential, it's called a dipole. Isn't that right? How can we therefore minimize dipole? Three things. One, we make the drain-to-channel capacitance small, namely make channel length long. But that's a non-answer because we're trying to make channel length small, right? That's non-answer, right? The two real answer is, yeah, what really is important is we want CD to be much, much less than Cox, so that the gate actually controls it much better than CD. It's a relative of these two, relative to the size of these two capacitors determine whether dipole is important or not. Is that right? Is that right? Does it make sense? And a lot of people can see, I'm sorry, yes, that's right. A lot of people can see this, by the way. Not many people can understand this. That's why we also, and therefore a lot of people can see we want a thin oxide. A lot of people can see that. Is that right? Yes? But not many people can understand why we also want a thin dielectric, why we want thin depletion layer thickness. Now you can see. Why? Because if we make the C depletion small, we're also minimizing the impact of ED. I'm sorry, if we make the C depletion large, we're also minimizing the impact of ED. Because these two are working hand in hand in this case. You follow what I'm saying? Such that we can even say, this is what we're looking for. All we want is C depletion much less than C oxide plus C depletion. That's what we're looking for. Is that right? Yes? Yes? That's good. So we want both these two capacitors large. This is different from the swing consideration. In order to get the best swing, do we want both Cox and C depletion large? We don't. We want Cox large, we want C depletion small, you see. So this is not subtle, but it's a very good picture. The three capacitance picture answers a lot of questions, including the question, how does CD, how does small channel length affect swing? I will let you think about this, all right? If you want to talk about it after this, about the break, we can talk about that too. I just use this to motivate you to think about this quality picture. Three capacitance, very simple. This can even tell you what does the channel length do to swing. That's a topic most textbooks don't touch. Right? In fact, no textbook touch because there's no known model to it. But you don't need a model. You can build your own model. How does the swing get affected by channel length? Think about that, right? Why it's not as sensitive as VT? But does that mean there's no effect? Right? Swing dependence on L. Think about that. Right? Good question. Do this as a term paper project. All right, any questions about this model? So this, I think, is a good qualitative model. If you want a quantitative model, go to that one. All right? I still have another slide to make it more quantitative, so let me finish this. You can think about it, and in the discussion, we can ask questions. Even more quantitative. Remember, yes?
How do you find CD?
Pardon me?
How do we find CD?
That's this now. Okay, now. In other words, can we think of CD simply as a parallel plate capacitance? No, you cannot. That's why this is only a quantitative model. If you want quantitative, go back to what we were doing now, going to earlier, okay? But we can interpret what we did quantitatively using that qualitative three capacitance. So if you want to know the quantitative meaning of that CD, we'll have to go back to the qualitative model, which is here. Let's look at it, all right? All right. Let's look at this, so then we ask questions in the discussion session, all right? Okay. So, I'm now rewriting this again, this time even in a higher level way of writing. Remember we have phi s, which is function of y, and L, and a VG and VD, remember that? I'm not copying it for you, but just remember we have that, right? If we have that, do you think you can find the VT just by forcing this phi s to be equal to 2 phi b, and then do the following? We have to do several things, sorry. First, we have to evaluate the f, meaning evaluate the phi s at the y where the barrier height is the maximum. In other words, we have to differentiate this with respect to y in order to find where we get the maximum phi s, right? To find the peak of this picture. You see what I mean? Yes? Once we find that, we call that peak, right? And equate that to let's call this peak maybe, huh? I'll add this word peak, right? right, at the maximum, right? And equate that peak potential phi s to 2 phi b. Yes? And solve for Vg. That Vg is our Vt. Do you see this concept? Yeah? Because now we have phi s as function of y and Vg and Vd. We just find out where that peak happens, number one. Then we evaluate the phi s at that peak. Then we get this peak barrier height. Equate that peak barrier height with 2 phi b. Right? And that can only happen at one particular Vg. That Vg is our Vt. Do you see that? This is where the math gets complicated. All right? You see what I mean? The physics is actually quite simple. The math gets complicated. So I'm not going to go through any of the math. Just say if you do approximation, you end up with this. Delta L is equal to this. Exponential. Let's not look like the parameter. Just look at exponential term. Turns out exponential function of L over L. Now, are you surprised to see exponential function of L over L? Hope not, because we did get hyperbolic sine, cosine, with a, which is essentially L, exponential function, right? The only reason we see exponential function is approximation. At the time when we wrote the paper, we thought, people will hate to use exponential hyperbolic sine function, right? It's better to use as the exponential function. There's nothing wrong. I do believe it's better because it allows people to use plots that can plot log of delta Vt against L, for example. We look for a straight line. This is a way to interpret it, right? So we use the exponential rather than hyperbolic function. But when we do that, we notice we need to take at least two of the Taylor expansion terms, not Taylor expansion now, expansion of hyperbolic function. Because we can expand the hyperbolic function into exponential functions. I mention this because it's really funny. So we propose that the delta Vt exponential function of L, channel length. And I think most people accept that, and it's a very good concept. I want you to remember that. But we just found out a few months ago the new version of BSEM 3, BSEM 4, because BSEM 4 uses a computer model for computer circuit simulation. We actually went back from exponential function to hyperbolic functions of L, because the users find out using that fits the data, Vt data, even better. So we used even BSEM 3 used this exponential term. Now we have gone back to hyperbolical function of L. So when things like that happen, again, you have to believe the model is a pretty good physical model. Right? It's a pretty good model. That model is actually so good that this exponential approximation is just not as good for circuit simulation as going back to that. But anyway, using exponential approximation, the equation becomes very simple. Delta Vt is exponential function of L with decay length of L, which has to do with offset thickness and Xt max. And pre-exponential term is Vds plus some constant, roughly equal to 1 volt. You make it very small. Suppose this is a large Vds. It's simply equal to Vds times exponential minus L over L. Okay? So during the break, maybe you can think about why is there linear relationship between delta Vt and Vds? How do you understand that? And secondly, can you then come up with some discussion about his question? That is, what determines CD, that drain to channel capacitance? Can you have some kind of qualitative answer to that? And the hint is that look at the slide here. All right? So we'll take 10 minutes break, and after that we'll hold our discussion session.